So now let's take a look at the third column here. So we mentioned that this is called an IP address. So an IP address is simply a way of uniquely identifying a device on the internet. And that uniquely is a bit of a white lie, and we'll see why later. But for right now, an IP address is just like your home address. So you need some way of identifying where you live. And if someone else has the same address as you, that's a problem, because then you don't know which place the letter should be sent to, for example. So now these need to be unique. So we can see here that these IP addresses look something like this. So this happened to be my IP address at the time, 10.251.202.239. So IP addresses will always be in this form here. There'll be 4 sets of digits, and each of those digits is going to range from 0 to 255. So actually, how many bits is that? So if I'm talking from 0 to 255, yeah, so this is going to be 8 bits. So that means if each of these things is 8 bits, and there are 4 of them, then how many bits total is this IP address? 32 bits, exactly. So that means that if each of the IP address in total is 32 bits large, that means that there has to be some upper limit on the number of IP addresses, right? Because we can't just keep tacking on more and more digits. So the upper limit on the number of these IP addresses is actually this number here, so 4 billion-ish. And so that, at first glance, that's a pretty huge number, right? We have 4 billion IP addresses. But then you kind of start to think, and the world's population is 6 or 7 billion, so that's already more than the number of IP addresses. And I, for example, on this podium have 2 laptops, 2 iPads, and an iPod, so that's 5 IP addresses there. And that's probably not too uncommon, right? You might have a computer at home, a computer at work, a smartphone, and each of these things needs an IP address if it's going to be able to be contacted on a network. So really, this number actually isn't so large. So when the internet was first started out, the engineers designing the internet probably weren't thinking about supporting upwards of 6 billion people on the same network. And so this actually was just kind of a short-sighted decision that was made. That at the time, 4 billion was like, nah, we're never going to hit that. It's totally fine. We'll just make IP addresses that large. And now, actually, today, we're starting to run out of these IP addresses because we have so many. And in fact, we already have run out. So this isn't the first time that kind of a short-sighted quote was made like this. So this is a quote from Bill Gates back in the 80s when he's saying that an IBM machine at the time had this limitation where it could support about 640 kilobytes of RAM. And people were saying, well, that's probably not so good. Bill Gates is rumored, he denies it now, but is rumored to be quoted as saying that 640 kilobytes of memory ought to be enough for anybody. So not the first time that we've made this kind of short-sighted decision. So these addresses here are called IPv4. So this is version 4 of the Internet Protocol, which we'll see next week, actually. So now there's actually a movement that's developing a new way of addressing computers on the internet. So right now, IPv4 is still widely used. And if you connect to a network, you'll be able to see your computer's IP address. When we say IP address, we're probably just referring to IPv4. But now we're actually starting to develop this other thing called IPv6. And IPv6 is basically just a bigger IP address. So IPv6 addresses, rather than that 1.2.3.4, which is kind of nice and easy to read, IP addresses look something like that. So now, rather than allowing just for 8 bits each, IPv6 addresses are actually much, much larger. So IPv6 addresses are actually 128 bits, which is much larger than just the 32. And that means that the total number of IPv6 addresses is that, which is a significantly larger number than 4 billion. And there's actually a website dedicated to letting you know how many IPv6 addresses are left. So there are currently that many IPv6 addresses, and we're projected to run out in that year, 5-something AD. So again, I think it's kind of funny that we may look at this now and be like, that's not even a year as far as we're really concerned. But the people designing the original internet may have looked at that number 4 billion and said, that's completely insane. Like, we'll just never hit that. So it's super, super interesting to see, this is kind of our short-term solution, because it's really not much of a long-term solution, just making the thing bigger. So we're probably just going to have to make the thing bigger down the road. It's just kind of interesting to think about, what's going to happen even farther down the road if we ever somehow use up all of these IP addresses. So there's an event recently, the IPv6 World Launch Day. And basically, where an organization was trying to get companies like Google and Facebook and CNN to switch all of their infrastructure from IPv4 to IPv6. Because eventually, if it's true that we've run out of IPv4 addresses, and that's a big deal because we can't uniquely identify things on the internet anymore. So we need to start actually switching to this new IP address system. That's going to require kind of reconfiguring all of the servers behind Google and Facebook. And so this was the second annual event in which this organization tried to get people to switch over. The slogan this year was, "This time it's for real," since last time it wasn't really for real. And so these are kind of some of the organizations involved. Well, we need the cooperation of people like ISPs, like Comcast, so that when you connect to their network, you actually are able to get an IPv6 address and use it. Then we also need other people like Microsoft and Google to allow their servers to be addressed with IPv6 addresses so that you can kind of share the same way of communicating with each other. So you can read more about the event on worldipv6launch.org. And if you're curious how successful it was, this is kind of what the IPv6 adoption is concerned. Looks like determined by Google. And so this looks really nice until you kind of zoom in on the scale here, and they're kind of 1%. And so this is saying that right now, about 1% of the requests that come into google.com are actually using IPv6. So that's nice. That means that Google actually supports IPv6. And if you're using it, then you'll be able to talk to Google. But while these actual numbers on the right-hand side aren't too impressive, what is kind of impressive is this growth here. So this curve is starting to kind of skyrocket upwards. And so this is kind of good news in terms of the adoption of IPv6. If this curve keeps kind of skyrocketing upwards, that means it won't be too long until a majority of the requests on the internet, or at least to Google, are actually using IPv6, which means that we're kind of moving towards adoption, and we're going to kind of hit this tipping point pretty soon if this curve keeps going upward like this. So any questions on IP addresses? So again, oh yeah, sure.
So I guess I'm wondering how exactly they're assigned.
Sure, yeah, we'll actually see that in just a moment, how we actually get assigned an IP address. So remember, an IP address then is just this way of uniquely identifying a computer. Because if I have two computers on the internet and I want to talk to one, I need some way of saying I want to talk to that computer and tell the network this is where I want to talk to. So we need to give that some address. Just like we gave, for example, addresses in RAM, these unique numbers. Just from 0 to something like 2 to the 32, or depending on how much RAM you had. Now we're simply giving them a different way, a different address. But again, they're really just numbers. So another way of kind of getting around this problem of having too many IP addresses are these things called private IP addresses. So when we said that an IP address uniquely identifies a computer on the internet, that was a little bit of a white lie, because you actually don't need a unique IP address to communicate over the entire internet. If that were the case, then we'd actually start running into some problems. But the reason that we're still OK using IPv4 is because this address doesn't actually need to be unique over the entire internet. So reason being, if I have a computer at home and some website, a computer at home, for example, is not going to power CNN.com. So I don't need to have the entire world be able to talk directly to my computer. Instead, what I can give my computer is something called a private IP address. So a private IP address is still this address, but it's no longer unique over the entire network, over the entire internet. It's now unique only within my small network. So that means that I may have a computer on my home network with an IP address like 10.0.0.1, but when I go to work, I'm on a different network. My computer might also have the IP address 10.0.0.1. So how does that work, right? That means how can I actually make a request to google.com and then have Google respond to me, right? Because in order for Google to respond to me, it somehow needs to send back some information, which means that it needs to send information again to some kind of IP address. And so if my IP address is no longer unique to the whole internet, this doesn't really make sense without some kind of middleman here. So first, let's just define what we mean by an IP address. So these three prefixes here are the common prefixes for an IP, a private IP address. So if you see something like 10.something.something.something, that's probably an IP address, and a private IP address. So similarly, if you see 192.168.y.z, that's also a private IP address. And so when we were allocating, as we'll see in a moment, as we were allocating all of the IP addresses available in the internet to different geographic regions, we basically said, OK, nobody is going to get IP addresses that start with either 10, 172.16, or 192.168, because we're going to reserve these for this private IP address thing. So that simply means, again, that if my computer has a private IP address, it's not unique over the entire internet. And a computer on another network cannot simply use my private IP address to communicate with me. So the way that we can use private IP addresses to connect with the internet is this thing called NAT, where NAT stands for Network Address Translation. And so what this allows us to do is actually change what my request looks like when it's coming from a private IP. So let's say that I'm on my home network, for example, and it looks something like this. So my router has an IP address. And this is going to be a public IP address that's unique to the entire internet, let's say. So I'm just going to say that my router's IP address is 74.125.26.228. I just totally made that up. It's just a random IP address. So now I have 3 devices connected to my home network. I'm an Apple fanboy, so I have a MacBook, I have an iPhone, I have an iPad, and I probably have some more Apple devices because I really like them. And each of these devices now does not have a public IP address. Instead, they all have private IP addresses. So I could have 10.0.0.1.2.3. Because this starts with 10.something, I know that this address is a private IP address. So all of these things are now connected to the router. And the router now is going to keep track of everything that's currently connected to it. So my Wi-Fi router that's probably sitting on my computer knows what's connected to it. And it's going to assign everything connected to it this unique number. So for example, my MacBook happened to get the identifier 1000. And that's simply going to be some way of uniquely identifying my MacBook from my router. We're going to call this a source port. And we'll see where things like source and later destination ports come in next week. But right now, this is simply a way of identifying my router being able to say that 10.0.1 is this unique thing. OK, so let's actually trace a request now. So I'm on my MacBook. I have a private IP. And I'm going to make a request to something like CNN.com. We know that CNN.com has to have a public IP address, right? Else there'd be no way for me to get there if it's on a different network. So CNN.com has a public IP address. And this is what's going to happen. So my request is going to go from my computer. As we saw, the first place it's going to stop is the router. So it's going to stop at the router. And the router is going to say, OK, I have a request coming in from 10.0.0.1. The router is going to ask, what is the source port for that private IP address? So it's going to look inside of this table that's just stored on the router, and it's going to look up this source port for this IP address. And so that's why, for example, private IPs have to be unique within this network, but not within the larger internet. Because if we had 2 private IPs that were the same on this network, the router would have no way of saying, what's the source port for this IP? So OK, so we're just looking up this unique number that the router is going to somehow need to use. So this is where the magic happens. After we look up this number, the router is actually going to change this request. So when I made this request, it said, I am coming from the IP 10.0.0.1, and I don't even know what a source port is, so whatever. Once it gets to the router is going to say, OK, actually, this request is coming from my IP, which is public, which is 74.125.26.228. So the router is actually going to modify the request that I made from my computer. It's going to wipe out where it's coming from and replace it with this public IP that is simply the router's IP. And it's also going to tack on this source port. So now the request that was made from 10.0.0.1 is now made from 74.something with this additional identifier. So now we're going to send along my request, and eventually it's going to reach its destination. So CNN.com now sees a request not coming from 10.0.0.1, but coming from 74.something, which is simply a public IP address. And CNN.com has no idea what device that this IP address is. It doesn't know if it's my iPhone, if it's my router, and it doesn't really care. It just needs to know where it should send the response to my client's request. So let's see what happens. So now CNN.com receives this request to this address, and it's going to forward it to some routers. And again, it's going to respond to the router's IP address. And again, it's going to make its way through the internet, kind of have some layovers on the way to its flight back to my house. And it's going to eventually reach the router at my house because that had a public IP address. So now the router sees a request coming in, and it's going to this IP address, 74.125.26.228. And the router knows, well, that doesn't really matter because I changed the request and I actually forged it, right? I'm lying. It's not actually going there. But we did send back this source port again because CNN.com sent back the same thing that I sent to it. So it's going to say, OK, forget that IP address. I know I have this unique number. I'm going to go back in to this table and use the source port to get an IP address. So if we back up, we're back at this table. Now the router is going to say, OK, well, I know the source port has to be 1000. What is the private IP that corresponds to that? It's going to be 10.0.0.1. So now the router knows where this request is actually going. It's not going to 74.something. It's really going to 10.something. So now the router can actually modify the request again and send it back to the original client that made the request. So now my request from 10.0.something went all the way to CNN.com, back to my router, and back to my private IP address. So that means that using this technique here, this technology, I was able to communicate with a public IP address without me myself having a public IP address. As long as I have some device on my network that all the devices can communicate with, then I'm able to do this. Because they can just send the request right to my router and not care about my private IP address at all. And CNN.com might not even know that I have a private IP address. So does that process make sense? Great. Oh, question?
So yeah, these designations of numbers of like the source codes, or I guess a better way to ask this is this true for all of us with our devices that they all have the same, like can I assume that my Android and my laptop all have the same public IP address?
Sure.
Number?
Sure, so that's a good question. So the question is, can I assume that all of my devices will have a private IP address and it could be the same? So the answer is it depends. So some networks have this thing called NAT enabled and some don't. Because for example, CNN might want to have a bunch of servers on their network, all that have public IPs, where at Harvard, for example, we don't really need that because my iPhone isn't a web server. So it totally depends on the network that you're connected to. And we'll see in just a minute how the network is actually responsible for giving you either a private IP or a public IP. And that's something you'd actually configure on the network when you're setting it up.
And also, when I go to, I'll bet when I go to CNN.com on my Android, it comes back with automatically the mobile version, So you said that CNN doesn't care, what device it's going to. So does that mean the router is somehow making that decision to show me the mobile version of that website instead?
Yeah, so that's a great question. So how does CNN, for example, send me back the mobile site? And this actually has something to do with something we're going to get to next week when we talk about HTTP. But basically, when we say that the router doesn't care, we mean that the router doesn't care where it's sending the information. What information is sent is a decision not made by the router, right? CNN.com is the one who decides, should I send you the mobile or the regular site? So it's actually, when I make a request to CNN.com, included inside of that request is going to be this little string called a user agent that says, I am an iPhone. Just so you know, server. You might not even care. I just want to let you know that I'm an iPhone. And CNN can then say, hey, because I want to support this mobile site, I'm going to ask, in every request, I'm going to look inside of the request, the actual contents of it, and say, are you an iPhone? Did you say if you're an iPhone? Because if you are, I'm going to send you m.cnn.com. So basically, that's something that happens at a higher level than just the simple communication that we're talking about now. That's a great question, and we'll actually see that next week.